Hello, D.
Hi, Professor.
Great.
I should have the billions of questions about the Derek's presentation, but I never get a chance to ask him.
You set up an appointment with him and have a Zoom session to discuss with him.
Yes, I already sent an email to him to request the slides of the Derek. Yes.
Great. Yeah, do it. So, let's see who else. Hao Yu is not there yet. So just to remind you, today is April 6th. Okay, April 6th. So great, everyone's here. So this is week 12 and lecture 8. So we already went through LTI system, and we point out that the stability condition for LTI system is not only necessary, but also sufficient. And we are going to go through BIBO stability and how that stability is linked to the impulse response boundedness. Then in the end, we are going to connect all the stability concepts and in the relationship between them. So this is in the internal stability in the Ruggs textbook. These are the reading pages. So we went through this LTI system, and we have A is a constant. We talked about the generalized energy concept, okay? Talk about Lyapunov function, okay? Lyapunov function. So there are three conditions a Lyapunov function should satisfy. It's upper bounded, lower bounded, and its change is negative semi-definite, meaning it will not increase, okay? And the Q here, if you don't have a very good idea, you just select the Q as I, okay, as I. Let's go. So if you can find a Lyapunov function, that means the original LTI system is stable in the sense of Lyapunov. And that stability is actually also uniform stability because it is not explicitly time varying. So there's no difference between uniform stability and stability for LTI sense. We also talked about exponential stability. So the procedures to check exponential stability is to make sure your Q is positive definite, and you compute the W. The W is positive semi-definite. Then it is stability in the sense of Lyapunov. If it is strictly positive definite, then it is exponentially stable. So we talked about Vx is xqx. It's a Lyapunov function for ax. X dot is ax. If somehow we can decompose the W into C transpose C equals this, then we can say this is very similar to construct the output is a CY, CX, Y is a CX, so Y is CX, is my output system. So then that is observable pair, AC is observable pair, so the system is exponentially stable. So we went through the proof, so quickly go through that. So this is again still proving the X. Okay, in the end, we need to prove that the size of X norm is bounded by exponential function. Okay, like this. Oh, wait a minute. So basically, we want to prove X norm square, okay, is bounded by the initial X0, okay, initial condition. So that is AC, whether it is an observable pair, okay, linked to the stability. So in other words, the choice of Q, no matter what Q is symmetric and is a negative semi-definite. It is not changing the stability results. So that is actually a very important theorem we talked about. So instead of checking whether A has all eigenvalues with negative real parts without solving the eigenvalues of A, okay, you only need to solve Lyapunov function, okay? So much easier to do. Again, the W is symmetric, it's positive definite, and Q is positive definite, okay? So if you can solve the Q from this Lyapunov equation, okay, using a MATLAB command, Lyap, to solve the Q and check the Q is positive definite or not. If yes, then A is a Hurwitz. So that is also unique, okay, also unique. So the proof process is here. So let's starting from here. This is a theorem. So if you want to check whether the A matrix, giving A matrix, whether all the eigenvalues of A matrix has all eigenvalues with negative real parts, okay. So that's a complex plane. So that means in here, nothing is on the imaginary axis. How to do that? So basically, you give a W, which is positive definite. You negative, then there's a negative negative definite. Then you solve, this is called a Lyapunov equation. Lyapunov equation. So Lyapunov equation. Then after you get the Q, you check the Q is positive definite. Then I know A has all the eigenvalues with negative real parts. So we can check that without solving the eigenvalues of A matrix. So this is actually beautiful, isn't it? Conversely is also true, okay? If A is Hurwitz, then you can choose Q, like given W, you can construct the Q and W will satisfy the Lyapunov equation. Okay. Lyapunov equation. Okay. So that's proving, we have proven. But remember, this is a basic quantity that all the eigenvalues of A has negative real parts. Then this one goes to 0 as t goes to infinity. So this is obvious. But if you don't see this is obvious, you can do what we have learned, model decomposition. Okay, model decomposition. And if you have another Q that is the same, satisfying the Lyapunov equation, then this Q and Q0 must be the same, okay? Must be the same. So that's uniqueness. So it's very interesting, isn't it? So exponential stability is basically your solution Q to the Lyapunov equation, positive definite, okay? So the procedure is you pick up a positive definite W. If you don't have a good idea, you just choose W as I. Solve this one for Q. test whether Q is positive definite. Do you guys know how to do manually checking the Q? Whether the Q is positive definite, PD? That's a basic skill to do that, okay? So if you don't remember how to check the giving matrix is positive definite or not, you can learn more from the linear algebra about how to check Q is positive definite. So starting from today, we are going to focus on IO stability. Okay. So IO stability basically says if my input is finite, output should also be finite, bounded, okay, bounded. So bounded input, bounded output is called BIBO. I hope you understand what we are doing here. And we talked about you have U, you have Y, but it should have some internal representation. It's called a state, okay, state, X, okay. By choosing the X, you can do a realization of the system. So from U to Y, Y is U times G. That's a in and out relationship. But from X, so you have X is AX plus BU, Y is CX plus DU. That's a realization, okay? The reason we don't have a minimum realization is we choose the internal representation X vector, not minimum. Not the minimum, okay? Not the minimum. So you have more variables included in this model. Therefore, you got non-minimum realization, non-minimum realization. Then you need to do a minimum realization for that. So for the BIBO, uniformity is implied, okay? We should not consider as dependent on the initial time 0. So it's nothing to do with my T0 here. So let's review about how to measure the size of a signal. So because we say bounded, so if a signal, this X of T is a signal, okay, usually it's X of T is a signal. Bounded, if you can find an upper bound such that for all T, the norm of X is a vector, okay? It's bounded by this M, so this is called uniformly bounded, okay? Uniformly bounded. So the norm of the signal, we said that for the all T, this suprema of the X norm T, for all T, the minimum one is that, okay? So nu is the smallest number such that this is greater than xt. Of course, you can say, oh, this infinity is also true, okay? So, but we need from here to here to check the minimum mu. Nu is upper bound the X of T for all T. So that's called a suprema, okay? Suprema. It's a minimum upper bound, okay? Minimum upper bound, okay? Infinite norm is norm on the space of bounded signal, yeah. So this infinite norm, okay, this is infinite norm is here. So it's a norm in the space of bounded signal. Okay. So you can understand this is a peak value. So this is like a peak value. So if you only have a scalar x, so you draw x of t, and this is t. So you have so these are the peak value. So because you need to do absolute value, okay. So then you need to put it down. So you should count both negative, positive, and do absolute value. So check The maximum one is the infinite norm for this signal. If it is a vector, then you need to use the norm, okay? So let's go back to this LTV system. We have learned that for LTV system, we can always write something like this, okay? Times U sigma. So this is kind of like mapping, okay? IO mapping. Well, in our response, we know that this IO mapping is written in terms of C on the left-hand side, B, and C is T, B is of sigma. This is my state transition matrix, okay? Phi T, comma, sigma. So for the uniform stability, the initial time T0 does not matter. Can take to be a negative infinity. So starting from a negative infinity, okay? That doesn't matter, whichever way you put. And now we are talking about the zero state response, okay? Zero state response, meaning the x0 is 0, okay? Zero state, yeah, zero state. But otherwise you should have a C phi x0, right? You have another term, you should add it in here, right? So, but we don't consider this term. We don't consider. So YT here is a zero state response, meaning the initial state is 0. So how we define the system is uniformly BIBO stable if you can find the upper bound n greater than 0. So remember, this all in the infinite norm, okay? Infinite norm, okay? The peak value, peak of peaks, okay? Peak. So the uniformity means this n is not a function of T0, okay? It's not. So the n is not changing for all different inputs. It's not it's not input dependent. Okay, if this is true, then everything will be nonlinear, right? But here we are talking about linear. So the system is uniformly BIBO stable if and only if. So remember, if and only if there exists a constant row such that, okay, is upper bound row such that this G mapping, okay, and the integration of that norm, okay, is less than rho. And remember, we don't forget this one, okay? Or we already said for all t, because I'll integrate this one. So this whole thing is a scalar, something scalar of t. It's a t function. Okay. So how we prove that? I think it's a good idea. We go through that. So let's assume we can find such a row. Okay, this row is given, exists. So then this row is, this is true. Okay, this is true. Okay, this is true. So that means my output is function of that. So it is also by this, by, you know, this is a summation of everything. Then is of course using a norm triangular formula. Say for example, like you have x times y less than or equals to x norm times y norm. So this is called triangular formula. Okay. And if you do, so this is true. If you do this is plus, this is also true. Okay. Of course, for any of the x of t, because this is for all t, it's bounded then by this maximum. So this is, by definition, is always true. So by doing that, I pick up the largest one. This U-finite, other people don't do anything. Just replace this one U sigma's U sigma. Then what do you have? You just replace U sigma with its maximum. Okay, it's here. Okay, put this one here. So you get here. Then this is a constant and nothing to do with sigma. So we are going to have this d sigma, okay, d sigma, and then ut is coming out. So coming out. Okay, but remember this whole thing, the integration is assuming here. Okay, so that is the rho. By definition, then this is BIBO already. So this is one-sided. So this is only if, okay? We should say if, okay? So, which is true, which is true. Okay. But remember, this is for all t, it's true. But I replace this one with a maximum in here, of course it's true. Okay, because this is one of them, okay? So conversely, system is uniformly BIBO, then we want to show whether the G T sigma norm and the D sigma and the T0 to T can be shown less than or equals to upper bound, okay? So here we are going to do a proof by contradiction. By assuming that it does not hold, then means this is unbounded. So unbounded. So because this is unbounded, I know that so this is a component of this one, okay? So the IJ there exists at least one component or more, okay? This component, I's column, I's row, J's column of this G, okay? Of course, we should write, okay? So G, let me see, why is this not working? This is G is Gij, Ij, okay? So that's the notation. So at least one of them is also unbounded. It's also unbounded. So that means for any of the row, okay, for any of the row, giving any of the row, I can find a t that is dependent on row, such that within the interval t0 to t row, this integral will be greater than this row, not less than, greater than. It's always greater than this row to violate that, okay? So that's based on assumption that this is not bounded, okay? It's not true. Okay, it's not true. Then I know this should be true then, okay? So then we're trying to talk about U. So for example, I find out the UJ sigma is sign of this one. I choose the sign of this. If it's positive, then it's, so why did they do that? Okay, it's because you have a freedom to do the U to define that. So if K, so it's just diagonal, okay, diagonal. So if it is not, so if it is K is not J, then it's all zero. Only this guy is not. What does that mean? That means I have something like Gij is something I want. Then I do a sign of Gij. If I have Gij times sign of Gij, that will give me automatically Gij absolute value. Make sense? So anything times its sign, it will be absolute value. Okay. So that's the trick. So therefore, we can get for all sigma, we can make the U sigma is 1. Okay. Because if you do absolute value, the sign will give you always 1. So in other words, you end up with at the T row side, yi will give you, this is my Gij, and this is my Uj. Wait, J, okay. I think this is J, is it? But it doesn't matter. The idea is you can form this absolute value in here. You can see the basic idea here. Okay. And this one will be greater than rho. We already know, greater than rho. Okay. And so at a certain point, because it's always greater than rho, then it adding other components. So of course, this will be bigger than the single component. Okay. Remember y square will be sigma yi squared, this I. So that is the two norm. Okay, so you can see that you giving any specific ones, the norm will definitely together the norm vector norm is greater than the single component, and it's greater than rho. Okay, so you can always have a bounded input, yet making the YT not bounded. So that means you cannot find a bound n to satisfy this. Therefore, the system is not BIBO, which is against our initial assumption that the system is BIBO. In other words, this assumption is wrong. Okay, so it's by contradiction. This is wrong. So this must be true. So that's proof by contradiction. So I hope you see all the logic flow in here. Okay. So then that's not true. It's contradicted with our initial assumption the system is BIBO. So therefore, we say the system is BIBO, then the G norm integral must be upper bounded. So that's for general LTI system. I hope this is clear. Okay. Give me a second. So let's go through an example. Can you take a look of this example and see whether you can get this transition matrix while I get my power supply here? So I suggest you take a look of this SISO system, single input, single output system, to see whether you can come out a transition matrix like this. I'm coming back with my power supply. Okay, so I'm back. Guys can hear? Everything should be fine. Okay. So you can see from here, our transition matrix actually can be solved by using this one, integration. So this is an LTI system, okay? So by doing that, you know how we do this is log this way, and then e to the power of natural log is very easy to get. You end up with this. Then you come to two terms. Then it becomes 1 plus tau squared divided by t squared plus 1. So that is the phi t tau. It's like this. So what we can say about this system, when t goes to infinity, okay, then, so this is my phi, then let's say for any t0, okay, and t goes to infinity, then this all goes to infinity. Okay, so it's a stable, the system is stable. And for exponential stability, we need something with gamma and lambda to bound this one, Okay, lambda t minus tau. So let's say tau is 0, okay, tau is 0. That requires, this is true, okay? This is true for all t. And obviously, it's not possible, okay? It's not possible, okay? So that means the system is not possible to be exponentially stable, okay? This is a little bit interesting for this system, okay? So this is an LTV system, stable, not automatically exponential stable. But for LTI system, if it is stable, it is exponentially stable. So let's check its impulse response. Okay, so this G is called a mapping. Mapping is also called impulse response. Okay, impulse response. So you have C phi B like this. So this is original LTI system. Okay, and remember, if you have this, so you have this t goes to infinity, this will go to infinity, okay, or goes to 0. So it's like the coefficient is gradually going, it's something like this. So this coefficient itself, something like this. It goes to infinity is infinity. It's 0. Then it's initially is 0. Or actually it's negative. Sorry, let me see if my pen works. It should be like something like this. Okay. So that's why it's always, because it's always negative, okay? Negative. It's always stable, okay? But I told you that last time we told you that you have AT in here. So if you have eigenvalue of AT, and so the eigenvalue, the real part of that, less than 0, okay? For all t, it still may not be true. This is a stable system, okay? Stable system. Like AT. Okay. I showed you some examples last time. But for CISO case, this is the case. That's true. Okay. Impulse response. Okay. So we have this one. CB is 1. So this is C is 1. B is 1. Okay. t is 0, t0 is 0, we end up integrating this tau replaced with sigma is here. Then the t goes here, so you are going to have something like this. This one will, t goes to infinity. Okay. You also go to infinity. It's not bounded. It's not going to less than some rho. No. No, I should say rho is not. So we should less than infinity. Okay. Which is not true. Okay, not true. Therefore, the system is not what? BIBO stable. So we have seen a case in here. Okay, a same case in here. So when it's an autonomous system like this, okay. So we talk about stability, exponential stability, and so on and so forth. But when you have input in here, you talk about BIBO, bounded input, bounded output. Even for a stable, original, or homogeneous system stable, it may not be BIBO stable. Okay, so I hope through this example you will see for any LTV system, stable of original system is stable with a control, it may not be IBO. Okay. So we have seen some surprises, but actually it's very useful to study the differences and the connections between different stability conditions. So when we talk about stability, what's the initial purpose? The initial purpose is talking about equilibrium point, how to characterize the behavior of equilibrium point. It is stable, it is uniform stable, exponential stable, or uniform stable, uniform exponential stable. And we also, in a sense, talk about asymptotic stability and EAS, uniform asymptotic stability. Okay. So this is all talking about the equilibrium point. Then this is for homogeneous system without forcing term. The forcing term is also called control. So if you have input signal already in there, so the whole system is inhomogeneous. Inhomogeneous. Homogeneous, EOUS. So then we need a notion of BIBO, okay? BIBO. So hopefully the system may be exponentially stable, but not BIBO stable if input output effectiveness is unbounded. What do we mean effectiveness? Okay. Okay. So the system may be BIBO, but may not be exponentially stable if it is not controllable, not observable. That's a possibility. That's a possibility. So let's see an example. Oh, this is so familiar to all of you going through the example I gave you. So this is what? Oscillator. So not exponentially stable. And in this case, it's not observable, ET, okay? But from in and out point of view, it's BIBO, the whole system, okay? So here, we come out something important. So assume the system is exponentially stable, and you have a B, T, C, T are both bounded, okay? Then the system BIBO is stable. It's BIBO stable, okay? So let me show you, then go back, show you what do we mean effectiveness, okay? Effectiveness. So remember, when we talk about the system, X dot is AX plus BU. So the control signal will go through the B to add in the system and evolve with the system, okay? Or Y equals CX, okay? CX. So this C and B is sort of effectiveness. So although you have a control signal in here, okay? So if this is 0, then you don't have effectiveness, okay? Effectiveness. The same thing is true here for this. If this is 0, it's not effectiveness, okay? So I hope you understand what's the meaning of the effectiveness. But now we say that effectiveness is somehow bounded, okay? Okay. And if original system is exponentially stable, then we can say the system is BIBO, okay? BIBO. Let's prove it. So again, this is for exponential stability. We know that this is a C5B, C5B. This G is a C5B, C5B. And the integration of that will be less than or equals to all of this. This is, I call it a norm inequality, okay? And remember, it's exponentially stable. So this is, C is bounded by mu, B is bounded by beta, and phi is bounded by these two guys with gain gamma and damping ratio lambda, okay? Damping ratio lambda. So then this G is, so you only have one sigma in here. So you just integration, then you have a lambda here as well, okay? And so T minus sigma, then you do a T0, then you are going to have something like this, okay? Something like this. So in other words, this has an upper bound. The G has upper bound, okay? The upper bound is this, and this is always positive. We can drop it, so it's bigger, okay? We can drop everything here. It's positive, so you drop this positive, this overall is bigger, so that's why you can see this is still true. So for the inequality, this is called enlargement. The enlargement of the upper bound. So this is smaller than this because it's 1 minus a positive number, you ignore that. So we know this impulse response G, the norm of its integration is bounded, okay? So that is the theorem, and we know if G is bounded, then it's a BIBO, okay? Is this one integration is bounded, then it's BIBO, BIBO. So this is like, if the system is exponential, if the system is exponentially stable, this is true, and B and C are bounded. So then this is bounded, so this is BIBO. So that's proving. So this is for one side, okay? So then only if is this side. If, then if is sufficient. Sufficient. And here is necessary. Okay. So then we need to say, oh, if it is bounded stability implies internally exponentially stable. So anything that gets large must be seen in output. So can excite anything that could get large. So how we can say that? Okay. So let's borrow something called empty symmetric. Okay, remember it's symmetric. And we call empty is PD. Okay, PD, positive definite, and it is uniformly, meaning has nothing to do with t, just meaning for any t, for all t, for all x vector. Okay, so this is supposed to be what? It's a quadratic form. Okay, this is a quadratic form. So x is a vector. Okay, x is a vector. So you can always bound this one from bottom with eta. Eta is non-zero, it's positive. Okay, so where's the size of my x? So that reminds you something with a Lyapunov function, right? But here we don't say that. We just say this is a lower bound. Then we call this is definitely, of course, definitely the positive definite. But because we can have this inequality here, m of t, and only you relate at eta, and eta is no longer contain any t here. So that's good. That's called a uniform. Okay. So now we're talking about system is uniformly controllable. Then we say there exists delta, that is sorry, W is a T delta. It's just small delta that the W is a uniformly positive definite in the sense of that. Okay, so that's our controllability gradient. And then uniformly observable means observability gradient with existed delta in here. Also, this is a uniform positive definite. Okay, now assuming that the state model uniformly controllable, uniformly observable, okay, and ABC all bounded alpha, beta, gamma, okay. So then the system is BIBO. System is BIBO if and only if it is exponentially stable. Exponentially stable. Remember, this is in generally not true. It's very difficult to say that. There are a lot of restrictions about controllability and observability. And at least you're from IO point of view. So you have IO, so you have state space. So state space is a realization of an IO, okay? And the state space here, you have to be both controllable and observable, okay? And this controllability and observability gradients must be uniformly positive definite, okay? So that's a very strong, very strong. So you among all the realizations, you need to pick up the minimum realization, yet you need to guarantee the gradients are uniformly positive definite. So the whole process is about 2-3 pages of proof. It's in the Rourke's textbook. So that's all on the time varying case. For LTI case, things will be easier. Perhaps it will give us more insights. We'll see. Okay. If the original system is controllable and observable, and the system is BIBO, if and only if it is exponentially stable. Okay. So this time varying theorem, it is true. Okay. So LTI is BIBO. All eigenvalues A have a negative real part, and all poles have negative real parts. So these are all equivalent or equivalent. They are all if and only if, okay? If and only if. So this one to this one, this one to this one, this one to this one, this one to this one. So all the if and only if are true. That's called equivalent. And also from here to here is if and only if, okay? So let's see a few examples. I think you should know what's this. Open left half plane is this side. Open left half plane is this side, okay? All eigenvalues. So this is a SISO case when we use the lowercase here. So that means this is a SISO case, okay? It's funny. A is 0, B is 1, C is 1. So they are all bounded, 3 of them. And in this case, e to the power of 0 is 1. This is my phi tau, okay? Okay. Bounded input, then this is 1. Bounded output is this one. I will give you also not true because what? We got a t in here. So in other words, the whole system writing is something like this. You have a u in here. I'm sorry. You have u in here. You have y in here. What's in between here? Okay. Don't you see that? It's directly integrating my, so you don't have this term, right? So you directly integrate the u. So this is just the integrator. So an integrator, you can see that a pole will be in here. Okay, you have a pole at the origin on the imaginary axis. So therefore, you have BI, but not BO. Okay, not BO. Interesting. Okay. So now I'm asking, so in fact, the output is just T integration of 1, okay? So this is unbounded. But the system itself, so this is just a counter example of OLHP. So this is not IRHP. This pole is not on the OLHP. So it's at the origin, only imaginary axis. So that's why you violate the BIBO condition. Okay, not BIBO. So before we do the summary, and let me say, what if you have S plus 1 here? Okay. So you have BI and BO. Okay, BI and BO. So if you have delta T is impulse, then you have sinusoid. Okay. So this is not BI. Okay. So this is BO. So we should not say that. We should say I gave you sinusoid. Okay, give you sinusoid. So this is a BI. You're going through another one like this. So you are going to have an output. So your output y t, it will be inverse Laplace transform of s squared plus 1 square. Okay. Okay. So this this is kind of interesting. I want to show you. So I want to show you something like this. So you have a system. your system is s squared plus 1, okay? So in this case, you still have eigenvalues in here. And remember, if you have delta t in here, so you have yt is, this is Laplace transformation is 1. So then it's a Laplace inverse of s squared plus 1. That will give you sine t, okay? Give you sine t, which is the yt will be less than or equals to 1, okay? Less than infinity. So it's a BO. That gives you an impression that if I have, let's say I give you sinusoid t to in this one, then will you give me an BO? This is BI. Can I get a BO? That is basically asking question about if my input is sine t, so my y of s is u of s times u of s times g of s. Okay, my u of s is s squared plus 1, and g of s, this is my g of s. So g of s is also s squared plus 1. So then I'm trying to ask, so what is my s squared plus 1 square, and that is my L inverse. Inverse Laplace transformation will give me y of t of this. This is the y of t. So is the y of t less than infinity for all t? Okay. So the answer is no. Okay. Because of the square, you are going to have t sine t somewhere. Okay, t sine t somewhere, and this t is still going up. Okay, so it's BI, not BO. So in other words, complex conjugate pair also shows up like not the OLHP. So the OLHP actually should write it here, this one. So that's for the LTI system. Let me review what we have here. So review for LTI system like this. So first of all, if you want to make this time invariant system BIBO, you have to be minimum realization, okay? Minimum realization is both controllable and observable. In this case, the BIBO and exponential stability, they are equivalent, okay? One implies each other, okay? So this proof is the same as what we did in the time varying case, So you can see stability from input-output point of view. So this is from IO point of view. Yeah, but why I come over here, it changed. Then I have to get to here to do point option ink color to this. Okay. So let's say uniformly controllable, uniformly observable, meaning for any time, okay? Then the state space model is uniformly controllable, observable, and all the bounded. The system is BIBO stable, if and only if it is exponential stable. Time variant system. So it's a good idea. We go to the textbook and see the procedure. It's about 2 pages. I gave an example about bounded input, not bounded output case for a pure integrator, okay? Pure integrator. But for a pure integrator, but for a sinusoid case, I also give you an example of bounded input, not bounded output. In other words, this OLHP is actually a very important concept. So let me go to the textbook. Go to the textbook. It's chapter 6. Okay, chapter 6. And they said in the page 208. Will be not chapter 5. Okay, 208 will be the output of stability. Are we on the additional stability criteria? Yeah, 208. I think the stability arrangement in the textbook is different to this orders of our presentation here. 208. Are they using the same? What is 208? Let me see. Table of contents. (208) is chapter 12. Oh, IO stability. Sorry, I kind of confused about internal stability. IO stability here. 208. Okay, here. So this is the theorem we are talking about, okay? So this is the theorem we are talking about. So you have a LTI system, LTV system, and ABC are all bounded, okay? And here is a state feedback, okay? State feedback. But it doesn't matter if your C is bounded. So here is the Gramian, okay? Gramian. The state equation is uniformly bounded input, bounded out, a state stable if it's only uniformly exponential stable. So in this case, they're only talking about state. The C is an identity matrix, okay? And Y is the same as. So it's called BIBS, okay? BIBS, bounded input, bounded state stable. We talk about BIBO. So then we need to have another C matrix, okay? So let's go from here. Okay. Wow, that's pretty long. So in this case, C is identity, okay, identity. In general case, C is not identity, okay. In this case, the observability grammar for steady equation is you have C transpose C in the middle. So here comes 210, page 210. So then you can see you have A, B, and C all bounded, and controllability grammar, and this is a controllability grammar, is observability grammar. They are all kind of lower bounded, so they will not be singular, okay? The state equation is uniformly bounded input BIBO bounded output stable. If and only if originally it is uniformly exponentially stable, okay, the original system. So I believe the proof they leveraged a lot of contents in the BIBS. So they did 2 steps. Okay, let me do. Let's walk through the BIBS bounded input, bounded state. This one. This one. Okay, a little bit bigger. Smaller. Bigger. That's too big. Okay. So let's do it this way. Yeah, so this is good. Let's do it. So again, because C is I, so we only focus on controllability grammar W. So is BIBS stable if and only if the origin system is uniformly exponentially stable. Linear steady equation uniformly BIBO stable. So we have phi B is, so the main thing is we try to find phi B, this impulse response. This one, this guy is, this thing is bounded, okay, it's bounded. So then we can say we can have this is bounded, okay? This is bounded. Okay. If this is bounded, then system is stable, not exponentially stable, by the way, yet. So AT is bounded. This AT is bounded is very strange to me. So you can, because AT is bounded, then you can assume this could be bounded, okay? So it's inside exercise. So then because of the lower boundedness of the controllability grammar, so you can do inverse is upper bounded, okay? Inverse is up bounded. This is interesting. Inverse exists. Then in particular, you have B, this one, inverse, then it's bounded. Okay, okay. So then you write this one in terms of grammar. This is just I. This is just I, okay? And grammar has a definition. Grammar has a definition, okay? Then you bring this everybody in because you are doing integration to gamma. Therefore, this can be bounded in this way. So then we try to integrate both sides, tau to t integration. So integration both sides on the second variable. So everything inside here. This can be further get to here. So that is IB can be proving. IB can be proving upper bounded. That's very tedious. So then this is bounded. So if this is bounded for all t and tau, so we have so-called uniform exponential stability of linear stability equation. So that's 2 pages long proof. Okay, so I suggest you go through this part to see. I still feel this is not beautiful. I don't feel this is beautiful. Do you understand? Because they want this thing to be bounded. I don't like it. I don't like it. There must be some nicer results out there. Okay, so I don't feel this is comfortable. This is okay. Yeah, this is okay. It's very strange. I never seen this AT is bounded. So it's chapter of the BIBO stability chapter. Okay. In nonlinear controls, BIBO stability is discussed differently. So time is almost up. What we are going to do next is the summary. So we did BIBO, we did minimum realization. Exponential stability is equivalent to BIBO. And that equivalence actually comes with a condition, okay? Comes with a condition. Okay, so let me review this condition for you. Okay. So the condition is for LTI system, sure, yes, BIBO is exponential. But for the time varying case, you need additional conditions, okay? What are the initial conditions? A, B, C are bounded, okay, as a matrices, they are bounded. And you have Gramians, should be controllability Gramian and observability Gramian must be bounded in certain sense, okay? So let me remind you, we are saying that this is in generally wrong, okay? In generally, this is not right, okay? It's not correct. This is only for LTI case, is correct. And BIBO stability, basically you need the impulse response. The G integral must be founded. So with that, the stability part, we have done all of them. And so I want you to see a picture here. So what we're talking is from beginning. Give me a second. We're talking about equivalent point and stability. And when you introduce input and how to check the BIBO, okay, stability. The question is, the original without input, the original system is unstable. Then introducing the input, you might bring the system become stable. Okay, so or to satisfy some performance index. Okay, so that's actually a very important part about feedback design. Okay, bring the state feedback idea in there. Okay. And state feedback is the foundation of output feedback. So sometimes because you wanted the state feedback, not all states are measurable. Okay, I say the states are internal to the system. So this Wednesday we're going to start state feedback. Okay. With that, we can take a rest, take a break, and we start at 6 o'clock. Do we need a help session? If we don't need.
Yes, we need.
Oh, okay.
I need.
Oh, okay. So I already prepared. The problem set 7 here. So yes, let's go for discussion. You guys take a break for about 15 minutes. I will come back maybe 6:05-ish. Okay. All right.
Mm-hmm.
So you still enter from within the CAT course. Okay.
Mm-hmm.
Okay. Bye bye. I'm going to end this, and we'll start at 6:05. Okay.